Good morning and good afternoon to all of you for joining our live webinar today, Insights and New Approaches in Transporter Characterization, SURFE²R. My name is Jason Villagomez, Marketing Manager at Nanion Technologies, and will be your moderator for today's event. Joining us as speakers will be Dr. Maria Barthelmess, New Approaches in Transporter Characterization, SURFE²R. Product Manager of the SURFE² family, Nathan Thomas, 50-year PhD student in Dr. Hensler Waldman's laboratory in the Biochemistry Department at the University of Wisconsin-Madison. His thesis focuses on characterizing the coupling mechanisms of the multi-drug efflux pump, EMRE, using a combination of functional and biophysical techniques. He has developed SSM-based electrophysiology reversal potential assays for higher throughput determination of transport stoichiometry. Additionally, joining us as the second speaker would be Professor Dr. Camille Perez, Assistant Professor Biozentrum at the University of Basel in Switzerland. Prior to his current post, he served as a postdoctoral researcher at ETH Zurich between 2013 and 2017, and from 2012 to 2013 at the Max Planck Institute of Biophysics. Upon completion of the presentation, we will hold a live Q&A session, and as such, welcome you to ask all of our presenters questions at any time throughout the webinar. You can log a question via the chat window found on the right-hand side of your screen. If you happen to experience any technical difficulties at any time, please inform us via the chat box. Additionally, today's presentation will be made available on demand shortly upon completion, inclusive of a transcribed copy of the Q&A session. I will now turn over the presentation to Maria for the start of the talk.
As an introduction of the two following talks, and especially for those of you who are not familiar with the method, I am starting this webinar with a 5-minute overview on SSM-based electrophysiology. What is SSM-based electrophysiology? Very generally speaking, it is a method that enables the measurement of very small electric transmembrane currents. This makes it suitable to record the activity of electrogenic transporter proteins. All right, we had a little issue. Okay. So SSM stands for solid supported membrane. SSMs are artificial lipid layers formed directly on a solid substrate. Here they are applied to form a special sensor that enables the detection of transport activity. The method was invented in the 90s at the Max Planck Institute and is meantime well established. And the Nanion SURFE² instruments N1 and N96 are implementing this method. So how does it work? A 3mm sensor is generated by coating a gold electrode with an SSM. Then a very high number of liposomes and membrane fragments or membrane fragments containing the transporter is immobilized on the sensor. During the measurement, the accumulated signal of all the protein on the sensor is recorded. And this is why it is possible to resolve very small currents. The transporters on the sensors are activated in a synchronized way by application of a substrate gradient with a fast perfusion system. It is also possible to load the vesicle in advance with a special kind of ions, and this way one can create even two substrate gradients for coupled transport modes. The substrate gradient drives the transport and leads to charge accumulation in the vesicles. The resulting membrane potential generates a current flow within the gold sensor, reflecting the transport current. what is the experimental scope of this? The method can be applied to investigate the function of electrogenic symporters, exchangers, uniporters, ATPases, and even some channels from bacteria, mammalian cells, or organelles. It is typically used to investigate the action of different substrates and to identify inhibitors. But it can also be used to investigate transport function and mechanisms. So, for example, it's possible to investigate coupling, environmental conditions, or sometimes even binding events. And finally, what's the experimental workflow? To perform an experiment, one has to prepare a suitable protein sample. This can be artificial liposomes or membrane fragments containing the transporter. Usually, the sample is prepared in a big batch and then stored in small aliquots until use. And at the day of the experiment, the sample is unfrozen and applied to the sensor with the SSM. After preparing all the sensors for the day, they are successively placed in the instrument, and for each sensor, a sequence of activation cycles is performed by the fluidic system. So you can measure, for example, a full dose response curve on one sensor, then switch to the next. With that, I will finish, and if this overview was too short for you, please be aware that we are planning a second webinar in June, where we are going to introduce the method and the instruments in more detail. We are actually even planning to run the instrument in our lab and to showcase a typical experiment. With that, I hand over to Nathan Thomas from University of Wisconsin-Madison, who will tell us about the investigation of transporter stoichiometry.
Okay. Thank you, Maria. Today I'm going to talk about this assay that I've been developing with the surfers to use this SSM-based electrophysiology to measure transporter stoichiometries. So, as many of you may know, as you work with transporters, the stoichiometry is, of course, a crucial determinant of the transporter function. So, for example, LAC-Y can couple the transport of lactose to transport of one proton. Under a physiological proton motive force, this allows a LAC-Y to drive approximately a 400-fold lactose gradient. In contrast, the protein PEP-T from Streptococcus aureus can couple 5 protons to dipeptide transport. So this means that under a physiological proton motive force, you can get a 10 trillion-fold dipeptide gradient. Now, these numbers assume tight coupling, and that is not always the case for transporters. In particular, the transporter that I work on the most, EMRE, we have seen recently good evidence from a variety of techniques, including NMR and other transporter assays, that EMRE is not tightly coupled. So I'm particularly interested in what transport stoichiometry really means in this context where you have multiple transport pathways. But, so anyways, I wanted to develop a transport assay to be able to measure EMRE. And this SSM-based electrophysiology really gives us a good method to be able to screen this quickly and easily, but we wanted to see if it was possible to actually be able to measure the transport stoichiometry with SSM electrophysiology. So the way that transport stoichiometry is often measured is with what's called a reversal potential assay. So this is a example that I will show you with the protein GDX, which is a proton guanidinium antiporter from E. coli, and it is a homolog of EMRE. So it's a good system to work out this transport assay for us. So if you have this tightly coupled transport equation where N protons are coupled to M guanidiniums transported, you can set up a transport reaction where you have a given either guanidinium or proton gradient, and then you can vary the an electric gradient using like a potassium linomycin system. And if you look at the direction of transport as a function of the electric gradient that you're applying with the potassium linomycin system, you can find a membrane potential where you don't get any net transport. So this is known as your reversal potential. And from this reversal potential, you can then calculate the number of protons and guanidiniums that are transported in a given transport cycle, which in the case of GDX is 2 protons per 1 guanidinium. So these traditional reversal potential assays are very well established. They've been used for decades. So why not just do this with EMRE? Well, in principle we could, but there are of course some drawbacks to these assays. So one of the main things is that these assays are technically difficult and very time consuming. It can be difficult to ensure that you have the internal solution that you want. If you want to change the internal solution, you of course need to do a separate reconstitution. You need some way to be able to monitor transport, whether that's through ion-sensitive fluorophores or radioactivity or some other method. And then under most conditions, you need a relatively large amount of sample, which can get expensive or difficult to purify. So we wanted to know if it was possible to essentially use the same setup and perform this experiment using SSM-based electrophysiology. So this next slide here, I'll just take you through the scheme for our assay. So what you can see here is we have, initially we have proteoliposomes with purified GDX. On the internal solution and the external solution are initially the same. And here we are, we're equilibrating our liposomes with 1 millimolar guanidinium at pH 7. So this is like our non-activating buffers. So the only currents you see here are solution exchange currents. There's no actual transport currents. Then for our activating buffer, we apply a proton gradient. So here we have a 2-fold outward-facing proton gradient. But under these conditions, we don't have any guanidinium gradient. So as I said before, there's 2 protons coupled to guanidinium transport. And so this forces 2 protons out, guanidinium in, which means that there's a net charge going out of the liposome, and so you get this negative signal. This is exactly what we expect. And so far, so good. And then as we do the non-activating buffer, you get the reverse transport to reestablish the internal solution of the liposome. Okay, so that's all fine and good. The proton gradient can drive the guanidinium transport as we expect. What we wanted to know is what if you then applied a guanidinium gradient? Could you actually drive uphill proton transport under those conditions? So again, we start with no gradient of either guanidinium or proton. Now, in our activating buffer, we still have the same 2-fold proton gradient, but here we're applying an 8-fold guanidinium gradient. This guanidinium gradient is enough to then drive guanidinium out and drive protons in. And so now we get a net charge moving into the liposome, and we see a positive current. And then, again, as we do the non-activating buffer, we get a negative signal. So this in principle shows that we can reverse the transport direction by applying like simultaneous currents or gradients of guanidinium and proton. Excuse me. And so if we do this as a function of different guanidinium gradients, we can see that we get this entire range of outcomes. So we can go from very negative currents where the proton gradient is driving guanidinium transport to very positive currents where the enormous guanidinium gradient is driving uphill proton transport. So next we wanted to see if this could be quantified to determine what the actual stoichiometry was. Now remember the published stoichiometry is 2 protons per guanidinium. So if we can go back one slide here. One common parameter that's used to evaluate SSM electrophysiology assays is the peak currents. And so if we plot this peak current, so the maximum current that we see for each of these traces, as a function of the chemical potential ratios, what we should see, if this is a good way to quantify this, is that the null potential or the null current would occur at the stoichiometry. So it should occur at this 2-to-1 rate in the middle. But we see that that's actually positive, and the null current is actually closer to 1.5. Now, this isn't necessarily all too surprising, because at the end of the day, peak current is more or less a kinetic parameter that, well, it is a kinetic parameter that often is related to the general activity or turnover rate of the transporter. So this could be convoluted by not just transport currents, but as smaller. So this is the Guanidinium potential where we where we would expect to see a null current. What you can see is that there is this initial positive current that's then followed by a little bit of a negative current. So what we thought might be a better way of quantifying this is to just integrate the entire activating current section. So basically we see between these 2 dotted lines. Now if you plot that integrated current, which is more of a thermodynamic parameter as a function of the chemical potentials, you can now see that we get null transport at the previously published 2-to-1 stoichiometry. Now we repeated this with 2 different concentrations of protein. So this is the same amount of lipid that we apply to the sensor, but different lipid to protein ratios. And we can see that this parameter is independent of the amount of protein that we apply, which is good. This is a good indication that we are seeing actual transport as opposed to just single turnover binding unbinding events. And then we also, of course, need to use negative controls here. So for GDX and for EMRE, there is a single glutamate residue that is responsible for binding both the proton and the substrates. So if you mutate that residue from glutamate to glutamine, you end up with a transport dead mutant. And so we can use that as a negative control. And both that and the empty liposomes, which just don't have any protein in them, don't show any transport. And so this pretty clearly can demonstrate that we get the transport stoichiometry that we expect from this assay. Now, another thing that would really increase the throughput of this assay, though, is if we could actually change the internal solution. So we tried to, we investigated this essentially by doing what we did before, where we reconstituted and prepared our sensors at an internal pH of 7 and 1 millimolar guanidinium. But then once we prepared our sensors, we could put them on the instrument, and then using the fluidics of the instrument, we can flow a different buffer over the sensor. And one nice thing that you have with this SSM electrophysiology is you can actually monitor the currents as you flow this buffer over your sensor. And so we can monitor this and just wait until we don't see any current anymore. So normally this took about 3 or 4 rinses. And so on the left here, these are the currents from our solution exchange. And so we wait until we get about a baseline current, and then we can repeat this assay at a different internal pH. And on the right here, you can see that the current from the third rinse is very negligible relative to the transport currents that we're monitoring. So this seems to be a pretty good indication that we've exchanged the internal solution. And then the even better evidence is then if we plot these integrated currents as a function of the ratios, we again get this 2 to 1 transport stoichiometry. So this seems to be pretty good evidence that we can indeed change the internal solutions on the sensor, which greatly expands the amount of experiments that we can do using this. So one thing that's a limitation of the current, again, the traditional transport assays using our traditional reversal potential assays is oftentimes, because of how time-consuming and technically difficult the experiments are, they're only performed under one experimental condition. So either one internal ion concentration and one internal substrate concentration. But this demonstrates that using this SSM assay, we can actually do this at multiple concentrations and test multiple conditions. So this brings me back to EMRE, which again, I'll remind you, we've seen evidence before that EMRE is not tightly coupled. So we wanted to see, what does EMRE look like using this assay? Now, as a disclaimer, all of the data I'm about to show you is preliminary with just a few replicates. Now we have, I'm pretty sure that on at least a qualitative level that all of this data is accurate, but we don't have the replicates to really say anything about quantitation yet. That said, let's go forward here. So what we've seen with EMRE is that EMRE's transport stoichiometry is dependent both on what drug concentration you use and on the pH. So with GDX, for example, when we changed the pH, we didn't see any change in the transport stoichiometry. But with EMRE, so on the right here, you can see that at neutral pH, it looks like it behaves somewhat similarly to GDX. So there's a reversal potential somewhere between 2 and 3. I'll just shift it a little bit to the right here. At lower pH, the shape of the curve is a little bit different, but it still does reverse. But at high pH, it seems to be completely uncoupled. So you can get, well, mostly uncoupled. So you get some changes in the currents as you change the external drug concentrations, but it never actually, you can never fully reverse the transport currents of the proton. And then similarly with the changing the different drug concentrations, as long as you have relatively low drug concentrations, you can get this nice reversal. But at higher drug concentrations, it again seems to be uncoupled. So this is interesting. And then I also just wanted to highlight one of the advantages of this method is that it's very easy and very fast. So for these pH effects, we were able to test 35 different experimental conditions in less than 3 hours using a very small amount of protein. All of this was done using a single sensor, so it's a single protein sample. But we can get reproducible results with this. So we can lower the pH and get the same results when we go back through the pH range again. So again, this is just one of the things that's very nice about this technique, is that we can get a lot more functional information about our protein in a lot of different conditions very quickly. Okay, so what the previous data shows, though, is that under normal physiological conditions, so relatively low drug concentrations around neutral pH, we still get reversals. So like the dominant pathway for methylTPP, which is a traditional MRE substrate, is indeed this antiport, so this drug-proton antiport activity that we expect. Again, this is exactly what we expect, but we have seen some evidence from NMR, for example, that MRE interacts differently with different substrates, and this can affect not only the binding affinity, but the transport rates. So what we were curious is, could we find some substrate that instead favored one of these other pathways? So a uniport pathway of either drug or proton, drug and proton, or a symport. So we could actually potentially even get driven drug uptake through these multi-drug transporters. So this would potentially give us a way to target these multi-drug transporters, which normally are like vectors for resistance, as instead a vector for drug susceptibility. So we performed just a quick preliminary screen of about 200 compounds. We were able to get one confirmed susceptibility substrate from this screen. But the screen was just an in vivo growth assay. So we wanted to know more specifically on a mechanistic level, what does this compound do? Does it favor this uniport pathway or a symport pathway? And so we can actually use this SSM assay to investigate that. So again, this is just a quick cartoon of how we're going to test this. So if you don't have any drug gradient and you have, but you do have a proton gradient, you should just get this, well, the observed current you'll see is just a downhill proton transport current. So in other words, it should be negative as protons go out of the liposome. Now, if you apply a very large outward-facing drug gradient, if the dominant transport pathway is antiport, then this should reverse the direction of the transport current. However, if the dominant transport pathway is symport, so you get the drug and proton going together, you won't reverse the current under these red conditions, but instead you'll need to have a large inward-facing drug gradient to then force uphill proton transport. So these are just some example traces. So on the left is methylTPP, which is a canonical EMRE substrate. And what we see here is that if you have this large outward-facing gradient, you can indeed reverse the direction of transports, just as we would expect for antiport. Now, what's interesting for our susceptibility substrate is that it doesn't reverse under this outward-facing gradient. It also doesn't reverse under this inward-facing gradient. So this indicates that our susceptibility substrate doesn't seem to be either a antiported substrate or a symported substrate. And instead, what we think it's doing is that it's increasing the transporter's ability to uniport protons. So in other words, it's causing an uncoupled proton transport. So it's kind of small on the slide, but what you might be able to see here, this dotted line here, is the proton transport current that we observe if there's no susceptibility substrate around, and then the other currents, which are much larger, are the currents that we observe when we have the susceptibility substrate around. So this is just a nice demonstration that even if we're not trying to get some exact stoichiometry, like quantitative stoichiometry out of this assay, we can still use it to get a nice functional characterization of the transporter. So anyways, so again, just to review some advantages of this assay, we no longer have any need for a fluorescent probe or radioactive isotopes. Really big advantage is that this is much higher throughput. So we can make hundreds of measurements on a transporter in a single day. It requires very little sample, so picomoles of protein per sensor. And then this, again, allows some very fast, easy screening of transporter function. With that, I'd just like to thank everybody in my lab and my funding sources. And then also, I just wanted to highlight my colleague Peyton Sprecher, who performed the compound screen where we found our susceptibility substrate. And with that, I will turn it over to Professor Camila Perez.